Hello, welcome back. Today we're going to be doing a video on Faraday's law. It's not going to be following a specific, it's going to follow a specific problem, but I'm really going to focus on kind of all of the different perturbations that you can have with Faraday's law. This week is exam week. The exam is on the 19th in class. And my review session will be, when you see it, it'll be tonight. If you're watching it on Tuesday, from 6:30 to 8:30 p.m. in cell 200 Southwest. That is the main collaborative study room, collaborative learning space in cell. So come by. I have a few things planned, but come with questions if you need them. We're going to be going over like your note card, stuff like that. But let's just get right into Faraday's law. So I have this set up here, and I have two things that I want to go over, but I'm going to kind of do this in a different way. I'm not going to go in with like a specific problem in mind. We're just going to kind of be going over what kinds of things you can see with Faraday's law. So right now I have a movable rail system. So the orange bits are conductors, and so there's no resistance in them. And then on the other end, I have a resistor of resistance R, and it is in a magnetic field. It's a constant magnetic field right now, and it's pointing into the page. So all those blue X's are the magnetic field, and they're pointing into the page. And right now I have a arrow that's saying that this one rail is moving to the right. So I really want to talk about what this is doing. So Faraday's law is the following. So it says that the change in the magnetic flux in a given time will induce an EMF, or you can think of this as like a voltage if you want to think about it in circuit terms. And what this really means is that this will induce a current. So another way you can think about this is how we can write we can rewrite this like this as well. So negative d dt, the integral of b dot dA. So this right here is the, So this right here is our equation for phi, our magnetic flux. And since we're trying to find the time derivative of that, the negative of that to find the EMF, I wrote it like this. So when we're thinking about Faraday's law, we're thinking about a change in flux over time. So what that can boil down to is there can be a change in the B field or a change in area. So in this particular problem that I have set up right now, let's start with the change in area. So right now, our loop that would be enclosed is this one right here. So it kind of goes right there. That would be our enclosed loop as we are looking at our at Faraday's law. So we want to think about a way we can rewrite this in terms of our changing area. So one way we can do this, so like I said, we can have an induced EMF based on a change in the magnetic field or a change in the area that the magnetic field is enclosing. So in this case, let's talk about the change in area. And just to reiterate, this is a surface integral. So just a quick reminder of what that looks like. That's a surface area. So when we have a change in area, so we're gonna assume that our area is, our loop is going to be perpendicular to our magnetic field, because that really makes it a lot easier to deal with. However, you can imagine it at some angle, with respect to the magnetic field. But let's say that I'm gonna make my coordinate system here. So this is gonna be X, this will be Y, and this will be Z. So we can see that our magnetic field is in the negative Z direction. And our area is changing. Our area is changing in the negative, or in the X direction. So basically what's happening is that this rail can move freely across these other two pieces of metal, these other two conductors. And so as that area is changing, it will induce an EMF, because our area that is enclosing our magnetic field is increasing. So when we have a change in area, let's say, so we want to find our change in our flux, right? So we have our equation right here that says negative d dt of the integral of b dot dA. But really, if we have a uniform magnetic field that doesn't change in time and our dA is remaining relatively the same, or we're starting with a finite area, such as this one that we have right here, we can just integrate these both out as constants. So what's that going to look like? It'll look something like this. So our E equals negative d dt b times A. If we were at some angle, we would add a cosine theta to that. But since we're perpendicular to everything's perpendicular to each other, the area and the magnetic field are perpendicular to each other, I'm just going to have it as BA. So if we have a change in area, let's look at, so we're going to look at our dA dt. So if our area is changing, that's what we're looking at right now. Our area at some point in time is changing. Right now, our area is defined by the length L and the width W. So I'm going to write, so our area is length times width, but we want to find dA dt. So I'm going to say dA dt, I'm taking the time derivative of the area, but what is changing in respect to with respect to these values right here? Well, we know that the width can't change because it's kind of stuck. The only thing that can move is this rail right here that's in the middle. So I'm going to say that our dA dt is now equal to dL dt W. Does that make sense? So as we're changing our length is changing as a function of time. So we're going to take the derivative of that, our change in the length, and our width remains the same. So our area is the thing that's changing. So that is how we could do that. So another thing that can change is our magnetic field. So I'm going to say once again that our induced current is negative d dt b times A. But this time we want d dt of b, dB dt. Now this can manifest in a few different ways. We can say that the magnetic field is increasing, and we can say that the magnetic field is decreasing. Okay. So we can have a change in magnetic field that is either increasing or it's decreasing. And most of the time, when you see these problems, they'll say that it's increasing or decreasing at a constant rate. And this is kind of code for linearly. So if you're given a start size of the magnetic field and an end time, you can find out how quickly it's decreasing over time. And you can do that using slope intercept form, just how you would normally do it in any algebra class. So like rise over run. So another aspect to these problems that is important is finding the direction of the induced current. So that comes from Lenz's law. So Lenz's law says that an induced electric current flows in a direction such that the current opposes the change that induced it. So in our, so for example, if we were to increase our area of our, if we were to increase our area of our loop that we have right here, then our induced current will want to oppose that. So since our magnetic field is becoming, our flux is becoming larger, it's going to want to make it become smaller. It wants to oppose that. So in order to, so our magnetic, so since our area would be becoming larger, it will want to become smaller. So our induced current will be going counterclockwise. And that is because what will essentially be happening is our flux will be becoming more positive. And so to counteract that, it will induce a current that goes this way, and it will induce another magnetic field because of this induced current that comes out of the board to oppose that magnetic flux, that change in magnetic flux. That's the most important thing. Lenz's law states that it's the change in magnetic flux that is important, not just the magnetic flux, but the change in it. So that's how we would do it if the area was changing. It would be, if it was increasing, then the induced current will be going counterclockwise because it will induce another magnetic field that points out of the board to reduce or to oppose that change in magnetic flux because the flux is increasing. We can also think about it in terms of the changing magnetic field. So what if we say that this magnetic field is decreasing? And if we want to take it a step further, and I know in this homework, in this exam problem that I have, it says like what direction is the, which direction should you be pushing in order for the bar that I have right here to remain in place? And so that can be also talked about in terms of Faraday's law and Lenz's law. And so what will happen is in this case, our magnetic field would be decreasing. And so in order to counteract that change in flux, it will want to induce a current that creates a magnetic field to make it go back to the way it was before. So in this case, our magnetic field is going into the board, but it's decreasing. And so we want to have a magnetic field or a current that induces a magnetic field that goes into the board to get it back to the way it was before. So our current, it kind of goes down like this, and then our magnetic field is going into the board. So it's going into the board, and that's exactly what we want. So now that we have the direction of our induced current as that is changing, we can look at our F equals I dl cross B. And this will show us what direction the magnetic force is in. So our dl in this case, the way that I have my coordinate system set up, my dl is in the negative y hat direction, and my magnetic field is in the positive or in the negative z hat direction. And if I do my little, so dl is in the negative y hat direction, and our B is in the negative z hat direction. So if we do our little trick with the cross products, DL cross B, we have a negative y and a negative z. So, but we're going in the same direction. So essentially what that means is that we're going to just ignore the negative y and negative z. And because we can always just take that out as a constant, and we are left with a positive x. So our force in the case where our magnetic field is decreasing is in the positive x direction. So it's going to be feeling a force that's going this way. It's going to be feeling a force that's going this way. So in order to counteract that force that it's experiencing, we want to push a force this way, F applied. So that's kind of like a little rundown of all of the different types of problems, the different situations that you'll see with Faraday's law. I hope to see you guys at the review session tonight, and I will see you later. Keep studying hard.